start with the shortcut. We start with the process that works every single time. And then we introduce the shortcuts as special cases, which is really what's going on here. So the shortcut that we're going to talk about today is called synthetic division. So we can use synthetic division only when the divisor is a degree 1 polynomial whose leading coefficient is also 1. That's why we don't start with the synthetic division, even though it's faster and easier. It doesn't work every single time, so we don't start with that as our baseline. We do the long division first. That works every single time, regardless of what the divisor looks like. And then we show you the synthetic division that works only in special cases, specifically when the leading coefficient of the divisor is 1 and the degree for the divisor is 1. So if we go back and we look at the problems from the sheet that we just got done checking for 8, 9, and 10, Hachi, what happened here? All right, well that's hard to read, but let's just get that out of there. Which one of these can we do synthetic division on? Can we do synthetic division on 8? I have to look at the divisor. Is that degree 1? Yes. Is its leading coefficient 1? Yes. Can I do synthetic division on this? Yes. How about 9? Yes. How about 10? If I look at the divisor, is the degree for the, what's the degree for the divisor? 2. Can I do synthetic division on this then? No. Everybody okay with how we can check to see if we can do synthetic division or not? Okay. All right. So let's look at an example, and in fact, let's just use 9 as our example. I'm just going to get that stuff out of the way. So what we're going to do is we're going to take the divisor, we're going to set it equal to 0, and we're going to solve. So when I do that, I get x equals -1. Everybody okay with that idea? Okay. So now I'm going to just do the synthetic substitution setup. Except I'm going to put that -1 on the outside. That's kind of what I'm going to be substituting in. Is everybody okay where these numbers have come from? Right, those are the coefficients for the dividend on number 9. Notice I didn't have to include any zeros because the dividend for number 9 goes to the 4th, 3rd, 2nd, first, and then C0, right? So now we're just going to do the same synthetic substitution process that we've learned earlier. So bring the 1 down. Negative 1 times 1 is negative 1. I add down, I get 9. Negative 1 times 9 is negative 9. Add down, I get 26. Negative 1 times 26 is negative 26. I add down, I get 24. And negative 1 times 24 is negative 24. I add down, I get 1. Guess what? We're done dividing. That was quick. I don't understand why we're done dividing, though. What did we just do? Well, here's what we just did. These numbers that we're left with here at the bottom tell us what the quotient and remainder are going to be. We're going to read those numbers from right to left. The furthest right number is the remainder. And then we have the constant term, the coefficient on the x, the coefficient on the x squared, the coefficient on the x cubed, etc., etc., etc. So our answer, we'd say, is x cubed plus 9x squared plus 26x plus 24 plus our remainder over our divisor. And we are done. Boy, that is nice, right? Compare that to when we did number 9 by hand just a moment ago. Much less space, much quicker, much less places to make a mistake because I didn't have to remember to distribute the negatives or any of that mumbo jumbo. That was fast and pretty nice, right? So, when at all possible, what kind of division would I like to do? The synthetic division, right? Yeah. Let's do it again here. Let's do the synthetic division for number 8. How's that sound to you guys? You don't mind. It's so easy. All right, so I'll start with my setup here. What number is going to go outside of the little bar here that I have to make? Positive 5. Everybody good with how we got positive 5? Set that equal to 0 and solve, right? And then as I write these across, 9, 12, 29, and then 30. So we're all set up. So we'll start our dividing. Oops. That's a negative 12 there. Looks like something's up. And then how do I interpret this? I go from right to left. So remainder, constant term, x coefficient, x squared, x to the third, and we just keep increasing 1 degree as you move to the left. However many you need to go up is however many you go up. It doesn't matter. So our answer then is 2x cubed plus x squared minus 7x minus 6. And because the remainder is 0, I don't have to do anything else with that, right? Well, that's pretty rad, isn't it? So fast. questions about this synthetic division? Okay. Good. The next topic that we're going to talk about is factoring polynomials. And this will be the last major topic in this chapter. Okay, just as a heads up, we'll spend more than a couple days here on this topic, as it's a big one, and it's, I think, builds on something that we had a little bit of a hard time with earlier, which was solving quadratics and factoring quadratics, because it's very similar to that process. And some of the processes are actually the same process or a modification of the same process. So it's a good chance to come back and review those skills there that, you know, were a little shaky for some of us. So we've talked about how to factor a quadratic, right? We're basically going to be looking at three situations here. The first situation is if I have two terms. So if I have two terms, there's three different factoring patterns I might employ. There's the difference of two squares that we saw earlier when we talked about quadratics. There's a difference of two cubes. Which is new. And there's a sum of two cubes, which is also new. So the way we're going to use these factoring patterns is we're going to look at the problem, and we're going to look for something in the problem that looks like one of these three. And then based on that, we're going to factor it using those as our rule. Okay? So let's look at some examples here. So let's say we have 4x to the fourth minus 25. Which one of these three factoring patterns seems to fit here? It should be a difference of two squares. Now you might look at that and go, but the first thing is got an x to the fourth in it. How is that a square? Right? Everybody probably thinking that? Well, how can I write 4x to the fourth as something squared? Well, 4 is 2 squared, right? X to the fourth is x squared squared. And 25 is 5 squared, right? If we write it this way, now it should be clear that this is definitely a difference of two squares. I have something squared minus something else squared. Can we see that now that I rewrote it? So you'll often have to use that trick to be able to identify your difference of two squares or difference of two cubes or sum of two cubes. Might not be quite as obvious as just staring you in the face, but you might have to do a little bit of rewriting. So in this case then, my value for a is 2x squared, and my value for b is 5. So I have a squared, or I have a plus b times a minus b. And I'm done. These should be the easiest of the factoring problems, because you don't have to worry about hunting for two numbers that do blah, 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 and blah, blah, blah. You just have to recognize the pattern and then figure out what the value for a and b are, and then you just apply the pattern. So let's say we have x cubed minus 8. What pattern does this look like? Well, the exponent here should be a dead giveaway, as it's going to definitely remove one of the possibilities, right? What can't it be? Can't be a difference of two squares, because a square's always got to be an even exponent, right? Here we have an odd exponent, so that one's definitely out. So it's either got to be a difference of two cubes or a sum of two cubes, right? Which one does this look like? Looks like a difference of two cubes. So x cubed, obviously we can write as something cubed, it's just x cubed. What is 8 as something cubed? What number cubed gives us 8? 2, right? 2 times 2 is 4. If I multiply by 2 again, I get 8. So here my value for a is x, and my value for b is 2. So if I apply the pattern, I have a minus b times a squared plus a times b plus b squared. If it's getting hard to see, you guys, somebody just stand up and turn off the lights. No big deal. If it ever gets hard to see, I encourage you to do that. It's more important that you can see the board or whatever. Okay? Caden, what's up? Oh, okay. Everybody still so far so good? Okay. How about this one? 27x to the third plus 64. What does this look like? Sum of two cubes. That's good. Okay. So 27x to the third, I need to be able to rewrite as something to the third. And 64 I need to be able to rewrite as something to the third. Well, obviously, x cubed is x to the third. What to the third power gives us 27? 3, right? 3 times 3 is 9. And if I multiply by 3 again, I get 27. Is everybody okay with that? And then what to the third power gives us 64? Four. 4 times 4 is 16. And then 16 times 4 is 64. So this is my A, and this is my B. So I have A plus B times A squared minus A times B plus B squared. Everybody so far so good? Okay. How about x to the fourth minus 1? What does this look like? Hopefully you said this looks like the difference of 2 squares. So what squared gives me x to the fourth? X squared. And what squared gives me 1? 1. So here's my A, and here's my B. So I have A plus B times A minus B. Am I done? Look at this one. What do you notice here? That's also a difference of 2 squares, isn't it? So the first one we can't do anything with because it's a sum. But that second piece can factor into x plus 1, x minus 1. So we need to make sure that when we're doing these problems, we're being careful that we are making sure our final answers can't be factored again. Everybody okay with that idea? Should we do another like that where we can get like more than one factoring that happens? Get a sneaky one here. Which pattern do you guys see here? Okay, I've heard somebody say difference of 2 squares. I've heard somebody say difference of 2 cubes. You're both correct. Which one should we do first? If you can do both of those two, you should do the difference of 2 squares first, because you get something that's kind of nastier to factor if you do the difference of 2 cubes first. So we want to do the difference of 2 squares first. That typically makes our life easier. Okay, so what squared gives me x to the 6th? X cubed. And what squared gives us 1? Well, that's 1, right? There's my A and my B. So I'm going to have A plus b times a minus b. Now what do you see? Yeah, we see a difference of 2 cubes and a sum of 2 cubes. Everybody agree with that? So in this one, the a is x and the b is 1. And here, the a is x and the b is 1. Kind of ran out of space, so I just wrote it underneath like that for you guys. Everybody hopefully can see why the a is x and the b is 1 in both of those situations, right? Okay. So for the first one, I have a plus b times a squared minus a times b plus b squared. And then for the next one, I have a minus b times a squared plus a times b plus b squared. Okay there? What if I had something like this? X to the 5th minus 1. Those of you looking at this and go, I don't see which one it's supposed to be, that's on purpose. It is none of them. The point of this was to illustrate to you that not everything with 2 terms is going to fall into one of these 3 patterns. So it is possible you have stuff that you can't do anything with. So just kind of keep that in mind. Now, if I'm giving you a bunch of problems to practice this, you better believe that most of them you'll be able to do something with. But it doesn't necessarily mean that every single one of these is going to have something you can do. Is everybody okay with that idea? Okay. Do we feel good about these 2-term problems? Again, not so bad. Just a bunch of these formulas to kind of play around with. All right, where are we at now? So the next situation is if we have 2 terms, I'm sorry, 3 terms. I wrote the right word, I said the wrong thing. So there's 2 things we might do here. And we're basically going to be using the same factoring technique that we did for quadratics. So if the leading coefficient is 1, we can just do kind of that short factoring. And if the leading coefficient is not 1, we have to do that kind of long factoring. And so again, let's look at some examples. So if I look at this, this to me looks like a quadratic. Now it's not exactly a quadratic because clearly this is a degree 4 polynomial, but it looks kind of like the quadratic pattern because if I look at the exponents on these two, actually really I want to look at the degree of each of these three. I have degree 4, I have degree 2, and then I have degree 0. Everybody see that? So, if I have a degree 0, and then my leading term, or the degree of the leading term, equals 2 times the degree of the middle term, that's really what I'm looking for. So I want a degree 0 at the end, and I want the degree of the leading term to be twice the degree of that middle term, which is what we have here, right? Because the leading term is degree 4, and the middle term is degree 2. 4 is 2 times 2. So that's what I'm looking for in order to use this kind of technique. Is everybody okay with what I am going to be looking for pattern-wise? How I'll know if something's kind of in this quadratic pattern where I can just use the same kind of quadratic tricks that I've used before? Okay. So here's the trick that I'm going to do. I'm going to make a substitution. And I'm going to suppose that y is equal to x squared. Why am I picking y to equal x squared? Whatever the variable on that middle term is what I'm going to set y to. So if that middle term was 7x cubed, y would be x cubed. If the middle term was 7x to the fourth, y would be x to the fourth. Whatever that middle term's variable is, that's what I'm going to set y as. Everybody so far so good? So if I make that substitution then, x to the fourth is the same thing as y squared, right? X to the fourth is is x squared squared. So it would be the same as y squared. And then I just have plus 7y plus 10. This is quadratic now, correct? How would I factor this? I just need two numbers that multiply to give me 10 and add to give me 7. Those two numbers would be 5 and 2. And then I don't want to factor over y, I want to factor over x. So my last step will just be to put the x squareds back in place of the y's. And that's it. Okay there? We'll stop here because it looks like we're about out of time. We'll kind of continue.